Good morning. Today, I want to talk and continue on our discussion of scientific notation. I'm going to make sure that everything's working. Looks good. So, last time we did 2.16, which was kind of introducing scientific notation. And it seemed like some people got a little bit confused and tricked by it. So, I'm going to kind of refresh our memory on kind of what it means, its purpose, and then talk about how to compare two different numbers that are in scientific notation. So, make sure you have your little heading on here with your name, date, and what it is. And then we're going to write our title up at the top, which is Comparison of Numbers in Scientific Notation. So remember that scientific notation is really useful and important when we are looking at numbers that are either really big or really small, because that way it's much easier for us to write it on the page and actually manipulate them. If I'm looking at something like the mass of the Earth, or one of those huge numbers that we had last time, remember, or if we look at the distance between Earth and Jupiter, which is a pretty far distance, be quite a road trip, is about 595 million kilometers. If I was working with this number a lot of different ways or in different uses, I would not want to continue writing this number out, because every time it takes forever. I had even stopped talking and count a little bit, and I'm fairly well versed in math. So instead of writing the number like this every time, we have our scientific notation, which is much easier. And if you remember how we do that, we take where our decimal point is in here, which remember is right here, because that's where our whole numbers kind of end, and we just move it up to the very beginning so that we have just one whole number before the decimal point. So I would kind of scoot it up here, over here, and then it would live right there, right after that 5. And then I can write 5.9, which I can say is much easier, but the problem is 590 million and 5.9 are very different. But what I can do then is just multiply it by 10 to that power. So I can count how many spaces I went. 1, 2, 3, 4, 5, 6, 7, 8. Okay, times 10 to the 8th. Because that's how many decimal points I actually moved it over. And I wanted to explain kind of, okay, great, that doesn't really matter, because I need to move my total decimal. Like, why does times 10 to the 8th even help and even kind of affect that? The way that this works is when I multiply a number by 10, that it moves the decimal point over. Remember, so if I take like 7 times 10, the really simple and easy rule I can use is I just move the decimal point 1 point over. So I can say that's 70, right? And if I do 7 times 100, well, that just means I move the decimal point 2 places over. That's 700, right? 7 times 100 is 700. So this is really like saying 5.9 times 10 with 8 zeros after it. So then I can just put 8 zeros after 5.9, which is exactly the same thing as moving the decimal place 8 spaces over. So I could go 1, 2, 3, 4, 5, but I did that already up here. So 5.9 times 10 to the 8th is shorthand for 590 million. And it's really, really much easier for me to write that. And in fact, in some engineering textbooks, they will even write this like this, 5.9 E8, which is even simpler, because notice it has one less step. Now, we're not going to be using that. You can use it in college if you want when you're taking your engineering classes, but my expectation is this when we're doing scientific method in class. Okay, so a little bit of a refresh, and then quickly, if I'm going to do a small number, so remember that number we used last time, let me go find it, was the diameter of an insect's cell was 1.7 times 10 Let me find the actual one because I don't want to. There we go. Times 10 to the negative 11th. Okay, so the question here is, why does, when you have a negative exponent here, why does it move the other way? Well, let me quickly kind of explain. If I take 10 to the negative power, I can write 10 to the negative 11th is the same as 1 over 10 to the 11th. Okay, so what that really means is I'm taking my number, 1.7, and instead of multiplying it like I did up here, I divide it because it's now like a giant fraction. So this really would be like 1.7 divided by 10 to the 11th power. And 10 to the 11th power is a 1 with 11 zeros after it. So it would be like 1.7 divided by 1 with 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And when I divide, I do the opposite that I do when I multiply. So instead of adding the zeros to the end, I move the decimal point this direction. So this number turns very, very small when this is negative. So negative equals small, and positive equals big. Okay? Quick refresher. Good to go. So now, my question, I'm going to go to the next page just because, I like murdering trees, and nothing like a good tree murder in the morning, I always say. Okay, question is then, if I have a bunch of these numbers in scientific notation, I have 8.8 times 10 to the 5th, I have 4.27 times 10 to the 12th, and I have 6.94 times 10 to the negative 3rd. Which of these is bigger, and how can I compare them and see which is the largest? Because I can just look at the numbers in front. 8.8 is bigger than 4, which is bigger than 6. So I know that 8 is the biggest, right? No. Here, it doesn't really work like that, because when we're comparing numbers, we're always looking at place value, because just like usual, place value is king. That's always the most important thing about a number when we're looking at a number. And when we get our place value from scientific notation, we get it from this times 10 to the something at the end. And that's where it really lets us know how big or how small this number is. So some of you might start to realize that, okay, so this really isn't 6.94. This is really, if I write 694, and I start with my decimal point here, I can go 1, 2, 3. It's really 0.00694. Is that number big or small? It is tiny, right? It is very, very small. Whereas these numbers up here are much, much larger. So our key for comparing numbers like this is looking first at our exponents and then at the numbers if we have a tie. So our rules for comparison. First, look at the value of the exponent first. Then look at whole number. So if I was going to sort these up here, my biggest number, if I go from greatest to least, let's make sure I'm not covering it up. I was perfect in there, wasn't I? Nice. So let's see if I put this up here. My biggest number is clearly 12, so I have 4.27 times 10 to the 12th is my largest. Then, which I can say is greater than my next number, which is 8.8 times 10 to the 5th, which is greater than my smallest number, which is 6.94 times 10 to the negative third. Oops. Boop-a-doo. There we go. So this is how I can sort and compare these numbers. And it's important to use when I'm looking at things that are really small or really big. And then lots of times I can see how much bigger things are. For example, if I was going to compare things that were really big. If I find, for example, the mass of the Earth. The mass of the Earth is mass. Oops, let me scoot this up. Is 5.9 times 10 to the 24th. And if we look at mass of the Sun, that gives me 1.98 times 10 to the 30th. Oh, does that mean the Sun is smaller because it's 1.98 compared to 5.9? Of course not. Look, this is 10 to the 30th. This is 10 to the 24th. The Sun isn't like twice as big. It's not 10 times as big. It's 6 orders of magnitude larger, which means that I would have to take the mass of the Earth and times it by a 10 with 6 zeros after it. So 1, 2, 3, 4, 5, 6. The Sun is at least 100,000 million. 1 million times larger. The Sun is at least 1 million times larger than the Earth. And I can take that easily by looking at these numbers. If I was going to look at something that was twice as big, then this first number would just be kind of twice as big times 2, right? But these show me that it's a massive difference between the two. Okay? Let's take a look at a couple of the problems. We'll do a couple of examples when we're going on. Okay, I've mostly done a lot of these examples, so I'm probably just going to do one. So let's take a look at number 1 and see how that goes. Number 1, or example 1, sorry. It says this, right? Less than, greater than, or equal to for each blank. We have 2.1 times 10, oops, that is small, times 10 to the 6th with a blank, and we have 8.9 times 10 to the 5th. Oops, the pen is a little weird. All right, which is bigger? Okay, what are my steps? Let's go find what my steps were. Okay, first, look at the value of the exponent first. Second, then, oops, that's a terrible N. No, I think I just made it worse. Then, look at the whole number to see what's bigger. Okay, first, I have 10 to the 6th and I have 10 to the 5th. Which is bigger? 10 to the 6th. Done. Okay, that one's bigger. Nice. One of the key things that you might remember, though, is if I'm going to compare these two numbers, let's look at this. Example 2. And if I'm going to look at 4.2 times 10 to the negative 8th compared to 6.7 times 10 to the negative 16th. So here I have 16 and 8. Oh, but I don't have 16 and 8. I have negative 16 and negative 8. Which one of these is bigger? Which means if I made my little number line here, which one of these is farther this way? Remember, I have 0, I have 10, and I have negative 10. Bigger is always this way. It is closer to the positive infinity instead of negative infinity on my little number line. So here, the bigger number is negative 8. Right? Because if I was going to mark this, oops, I would not be there. It would be negative 8 would be here. This would be negative 2 or so. And my negative 16, oops, would be way back there. And that is much, much smaller. So in this case, this one is larger. Okay? That should be good. Good luck. And see what you can do.